Welcome. My name is Molly Horseman, and I am a faculty member at the VA Quality Scholars Coordinating Center at the Michael E. DeBakey VA Medical Center. This Methods and Analysis mini-module was developed in conjunction with VAC's Methods and Analysis faculty, Dr. Susie Miltner and Dr. Brant Oliver. This mini-module will provide an introduction to statistical process control. Statistical process control is a powerful tool that enables healthcare improvement teams to understand the stability of prior system performance and to predict future performance. The type of statistical process control chart you will use depends on the type of data that you are analyzing. Although there are numerous statistical process control charts to choose from, this mini-module will focus on two of the most common types of statistical process control charts used in healthcare improvement: the XmR or eye chart and the P chart. There are two types of variation that we look for in healthcare improvement: common cause variation and special cause variation. Common cause variation is the random variation that happens by chance alone. This variation does not represent a statistically significant change. In statistical process control, common cause variation means that system performance is predictable. Special cause variation is non-random variation that can be attributed to an assignable cause. Special cause variation is a statistically significant change from the average performance of the system. In statistical process control, special cause variation means the system performance is not predictable. Determining the type of variation you have is important because it helps you determine what your team needs to do to improve system performance. Special cause variation may be evidence of process improvement or evidence of process degradation. Whether special cause variation is positive or negative depends on the context within which you are working. If you have special cause variation, you will use your understanding of context to determine if it is a positive or negative change. If the change is desirable, your goal will be to understand the assignable causes to maximize, optimize, replicate, and standardize the change. If the change is negative, your goal will be to understand the assignable causes to minimize or eliminate these changes. Once you change the system, you may get to a state where the performance is predictable and you have common cause variation. If your system is predictable, it is important to consider whether your precision and your mean performance is acceptable. If the range is too wide, you will want to work to make the process more reliable and increase the precision. If the mean performance is unacceptable, you will want to redesign the process to get a better result. Both of these actions may eventually lead to statistically significant changes in system performance, and the cycle would continue. In this mini-module, we are providing an introduction to statistical process control charts. Statistical process control charts are also called Shewhart charts, after Walter Shewhart, an early leader in using statistical methods to measure processes over time. The structure of statistical process control charts is similar to run charts. In statistical process control charts, the x-axis is time-ordered data, and the y-axis is your variable of interest. Like the run chart, there's a line of central tendency. However, one of the key distinctions between the run chart and the statistical process control chart is that the run chart uses the median as the line of central tendency, and the statistical process control chart uses the mean or the average of the data as the line of central tendency. One of the most notable differences between run charts and statistical process control charts is that statistical process control charts have control limits. The control limits are 3 sigma deviations above and below the mean. 3 sigma deviations is slightly less than 3 standard deviations. 3 sigma deviations is roughly equivalent to 2.67 standard deviations. The term 6 sigma in Lean Six Sigma comes from these control limits. If you have a process that is performing within the upper and lower control limits, you have a process that is in 6 sigma control. Next, we are going to review the rules for detecting special cause signals in statistical process control charts. Although there are many rules that have been developed to analyze statistical process control charts, our focus will be on the 3 basic rules that you will use most often: shifts, trends, and single points outside of the control limits. It is important to note that you only need one of these rules to be positive to have special cause variation. In this mini-module, we will be using the special cause signals found in the Healthcare Data Guide. These are the same special cause signals used by the Institute for Healthcare Improvement. The first special cause signal to look for is a shift. For statistical process control, shifts are defined as 8 or more consecutive points, either all above or all below the mean. This is different from run charts, in which only 6 or more consecutive points above or below the median indicates special cause variation. Remember, we do not count points that fall on the line of central tendency, so a point that is exactly on the mean does not break a shift or add to the number of points required for a shift. In this example statistical process control chart, we see that there is a shift starting at July 17th with 8 consecutive data points below the mean. The second special cause signal is a trend. Trends are 6 or more consecutive points, all going up or all going down. This is different from run charts, in which only 5 or more consecutive increasing or decreasing points is needed for special cause variation. When there are 2 or more consecutive points that are the same value, remember that only the first point is counted towards the trend, and the repeating values are not counted. Going back to our statistical process control chart, this is an example where at first glance you may think there's a trend. However, there are only 5 consecutive data points that are all going down from July 15th to July 19th. The 6th data point is increasing. Thus, this chart does not show a trend. The third rule for special cause signals and statistical process control charts is having 1 or more points outside of the upper or lower control limits. This is a powerful signal for special cause variation and was the primary special cause signal used by Walter Shewhart. The point outside of the upper and lower control limits is one of the main differences in the detection signals for special cause variation between statistical process control charts and run charts. For this rule, it is important to remember that a point that is exactly on the control limit is not considered outside the control limit. Unlike run charts, the presence of too many or too few runs is not used as a detection rule in statistical process control. Looking at our example again, we see that there is 1 point outside of the upper control limit on July 2nd, which provides a signal that this statistical process control chart is demonstrating special cause variation and that system performance is unpredictable. Remember that once you've identified special cause variation, you must then determine if the special cause variation is positive or negative based on your knowledge of the underlying context. If the change is positive, you will want to work to maximize, optimize, replicate, and standardize the change. If the change is negative, you will work to minimize or eliminate the change. If there are no special cause signals in your statistical process control chart, the system performance is said to be in statistical control. This means that there is no statistically significant variation from the average value, and that all the points are within the control limits. The near future performance of the system can be predicted within a less than 5% error rate. This ability to predict future performance can be incredibly helpful to improvement teams. If the system is in statistical control, and if you have no changes to the system, you can confidently predict that the process will continue to perform at the same level with the same average and with values falling between the control limits. Remember, just because something is in statistical control does not mean that the system is performing well. It simply means that in the absence of any changes to the system, that the performance of the system is predictable. Unlike run charts, there are several types of statistical process control charts to choose from. The first step is to determine what type of data you have: attribute data or variable data. Attribute data is non-continuous data. Attribute data includes classification data, in which things are categorized into one of 2 categories, and count data, in which the number of times an incident happens is counted. Examples of attribute data include a count of the number of falls on a specific unit and the percentage of patients who receive appropriate cancer screening. Variable data is continuous data. Continuous data is quantitative data that uses a measurement scale. Variable data includes clinical measures, such as patient weights, and operational measures, such as the number of patient visits or hospital length of stay. In this mini-module, we will review P-charts and XmR charts, which are two of the most commonly used statistical process control charts in healthcare improvement. P-charts are an attribute chart that can be used with classification data. You can remember the type of data included in P-charts by thinking of them as proportions or percentage charts. For P-charts, your data will have a numerator and a denominator. The denominator will be the total number of individuals in a defined population. The numerator will be the number of individuals in the defined population who can be classified into one of two categories. For statistical process control, this is known as classifying non-conforming units. For example, imagine your improvement team is interested in the in-hospital mortality rates at your facility following cardiac surgery. The denominator would be all of the patients undergoing cardiac surgery, and the numerator would be the number of those patients undergoing cardiac surgery who died in the hospital. This will give you a proportion in which the numerator, number of patients who died, cannot be larger than the denominator, which is the total population of patients undergoing cardiac surgery. The appropriate statistical process control chart to analyze this data would be a P-chart. XmR charts are used for continuous data. You may also see XmR charts referred to as eye charts or individual charts. For the XmR chart, each data point consists of one observation of continuous data. Imagine that your improvement team is interested in reducing the amount of time it takes for patients to get from the OR to the ICU following cardiac surgery. You can measure the time it takes for each sequential patient undergoing cardiac surgery to move from the OR to the ICU and analyze that data using a XmR chart. Next, we are going to look at the XmR chart and P-chart in more detail. Here's an example of a XmR chart. As you can see, the XmR chart consists of two charts, the X chart on the top and the MR or moving range chart on the bottom. The X chart is a plot of the time-ordered data. In this example, the X chart is a plot of the sequential daily fasting blood glucose levels for a single patient. The line of central tendency in the X chart is the mean, and there are upper and lower control limits, which are 3 sigma deviations from the mean. The moving range chart is created from the absolute value of the difference between successive data points on the X chart. For example, the first point on the moving range chart is the absolute value of the difference between the first and second points on the X chart. The second data point on the moving range chart is the absolute value of the difference between the second and third points on the X chart. The moving range chart can be helpful for 2 reasons. First, the moving range chart provides an estimate of precision. The R bar is the average amount of variation in the data. Second, the moving range chart includes an upper control limit. Points above the control limit indicate that there is a statistically significant greater amount of variation at that time point than would have been expected by chance. The control limits for the X chart and the MR chart are calculated using the average from the X chart, indicated with the X bar, and average moving range from the moving range chart, R bar. These calculations create straight control limits for XmR charts. You can also see from the equations how variation impacts the width of the control limits. A smaller R bar will result in control limits that are closer together. A larger R bar, which indicates greater variation, will result in wider control limits. To create a XmR chart, it is recommended that you have 20 to 30 data points. Control limits that are created with fewer than 20 points should be considered trial limits. The P-chart is similar to the XmR chart, but it has some important differences. Like the XmR chart, the P-chart includes the mean as the line of central tendency, and there are upper and lower control limits. Unlike the XmR chart, the control limits on the P-chart are not straight. The control limits on the P-chart fluctuate based on the size of the denominator for each data point. Recall that P-charts are used for proportions or percentages that have a numerator and a denominator for each data point. The P-chart will adjust the control limits point by point based on the size of the denominator. This is a notable difference from XmR charts, where the control limits are calculated based on the average moving range. Like confidence intervals in traditional statistics, as the denominator size increases, the width of the control limits decreases. Conversely, as the denominator size decreases, the width of the control limits increases. As you can see from the chart, the denominator at week 16 is smaller than the denominator at week 19. We can tell this because the width of the control limits at week 16 is greater than at week 19. Remember that with a p-chart, you can quickly examine how sample size changes over time by examining the control limits. Next, we are going to go through a few examples of statistical process control charts. Imagine you are working in a clinic and are interested in the average amount of time patients spend waiting for their appointment. Your first step is to determine which type of statistical process control chart is appropriate for your data. Take a moment and decide which chart you would choose for this data. The answer is the XmR chart. The average clinic wait time is continuous data, which makes a variable data chart appropriate. In this case, there is one value, the average clinic wait time, per data point, and the best chart to choose is the XmR chart. Next, your facility provides you with data on average clinic wait times for the past 20 weeks. How many special cause signals are there in this X chart? Remember to look for shifts, trends, and points outside of the control limits. The answer is 3 special cause signals. There are 2 points outside of the upper control limit and a trend with 7 data points all decreasing. Each point outside of the control limits counts as a separate special cause signal. Remember that you only need one special cause signal to have a special cause variation pattern in statistical process control charts. Because this chart has special cause variation, it is not in statistical control. As you may have noticed, we have not included the moving range chart with the X chart. Although the average moving range is used to create the control limits and is helpful to understand variation in the data, only the X chart is used for the detection of special cause signals. Next, imagine that you are working as part of an interprofessional team on an inpatient medicine unit. Your facility is interested in patient flow and would like to increase the number of patients discharged before noon from the general medicine service. Take a moment and decide which chart you would choose for this data. The correct answer is a p-chart. In this case, your data is a proportion. The numerator is the number of medicine patients discharged before noon, and the denominator is the total number of medicine patients discharged from the hospital. A p-chart is the most appropriate statistical process control chart for this data. Next, you are provided data for the proportion of medicine patients discharged before noon for the past 20 weeks. You can see the fluctuating upper and lower control limits, which are characteristic of a p-chart, and indicate that the sample size in the denominator is varying for each data point. How many special cause signals are in this p-chart? In this case, there are 2 special cause signals, 2 points outside of the control limits. Because there is special cause variation, this system is not in statistical control and it cannot be used to predict future performance. Remember that statistical process control charts help us to understand system performance. If there is special cause variation and statistical performance is unpredictable, the improvement team will need to identify the assignable causes for the change and take appropriate action. If there is common cause variation, the system is stable and the performance is predictable, but improvement teams will have to determine if the performance is acceptable. If not, teams can work to make the system more reliable by increasing precision or redesign the process to get a better result. In this mini-module, we have learned about two of the most commonly used statistical process control charts in healthcare improvement. In future mini-modules, we will explore the statistical process control charts used for count data and for continuous data when there is more than one observation per data point.